All right, great. So now the final talk today is by Henry, and he's gonna continue with his second lecture. Take it away, Henry.
Great, thank you, Shita. Good. So last time we laid a bit of groundwork that's going to help us build an evaporating black hole today. So we finished last time with a discussion of JT gravity, and in particular this Shortian theory. I promised a brief discussion about symmetry breaking, but I think I'm going to skip that and interest in getting on some of the new things about baby universes later. But the first thing I'll say is I've got on the Slack channel, there's at least the first part of the notes that covers the material from yesterday and sort of probably a good chunk of what's from today, and I'll try to update that as much as I can. In particular, this stuff about symmetry breaking in the Shortian, there's a section in that, so you can look there if you're interested, and sort of comments on the notes and things are very welcome. And good. So right. So we've got this theory in hand. We know what the degrees of freedom are of this JT gravity theory, and we have our conformal matter theory that's in particular, it's been very simple to solve for the dynamics of energy momentum, and we've got this simple way of coupling to an external system. So now it's time to put it together and actually find what a quantum black hole looks like, which includes quantum matter effects. So first of all, I'm just going to give talk about the semi-classical approximation in general. So we've got, in general, we'll have some gravitational action that depends on the metric, and in this case, for JT, the metric and the dilaton. And then we'll have some matter action, which is going to, first of all, it'll depend on the metric, because of course the matter propagates on the background metric, but also on some matter fields. And we'd like to solve this theory. Now, of course, doing the full path integral for a gravitational theory and it's going to be very difficult. And even for something as simple as JT gravity, really solving this sort of thing explicitly as a fully quantum theory is, of course, an extremely hard problem. It could be potentially is doable for JT, but for us, it's we're going to try to do something a little easier. So you'd like to make some kind of semi-classical approximation. So we want to look for saddle points of this action. If you just look at saddle points of the whole action, it's the gravitational action plus the matter action, then this is going to miss important physics. So you might like to think of the matter action maybe as being a free boson. And if you look for saddle points, then you're going to just have some classical matter background. And in particular, you're not going to produce Hawking radiation. So it'll take my pen a couple of minutes to wake up. So in particular, Hawking radiation is what we miss. So we need to do something that's in between the two. We're not going to do the full path integral, but we're not just going to do a classical approximation. So that's where this semi-classical approximation comes in. And the semi is that it's going to be half quantum and half classical. So the quantum piece is going to be the matter. So we're going to treat the matter sector fully quantum mechanically, and the gravitational piece we're going to treat classically. So one way to say that is that we, first of all, solve the matter. Of course, even this is a very difficult problem most of the time, but for our conformal theory, in many cases, at least we can calculate most things, but at least formally, you can imagine completely solving the matter on any fixed metric. Maybe at this point, I'll just emphasize that our matter theory for our CFT, it's going to propagate on the background metric G, and it's not going to be sensitive to the dilaton at all. So it's going to depend on that, on the metric I call G rather than some combination including dilaton. Okay, so we, at least in principle, we do this path integral, and that gives us this effective action. So this effective action, you should bear in mind that this is not going to be a local action anymore. if our field was very massive, then it might be local on scales much bigger than the inverse mass, but for our CFT, that's not going to be the case. So we've got some non-local action, but something we can compute, at least in principle. And once we've got this non-local action, then we can look for saddle points of the gravitational action plus this matter quantum effective action. And in particular, we want to ask what the saddle point equations are of this, the thing that's going to determine our saddle point. And of course, the gravitational piece is just going to be given by the Einstein tensor in Einstein gravity, or the equation for the dilaton that we had earlier for JT. But now varying the effective action, by definition, that inserts a copy of the stress tensor. So if we vary the metric, some component of the metric at a point X, then by definition, that is the same as inserting a stress tensor operator at the point X. So that means that you end up sourcing Einstein's equations by the stress tensor. Okay, so that's a semi-classical approximation. One comment I'll make is that in JT gravity, this isn't a problem, but in say maybe GR in 4 dimensions, we want to actually allow Hawking radiation to come from gravitons themselves. So if we wanted to include that, then this effective action would need to include one loop effects from the graviton. So we actually have to it's slightly more subtle, but this should include metric fluctuations at one loop. So one way to do that in, say, a short chill black hole, some spherically symmetric situation, is that you think of the gravitational action as this gravitational piece that we treat classically as being a set of spherically symmetric configurations, and then and then fluctuations in the transverse direction you would treat as quantum matter at one loop. But that's a technical point that we don't have to worry about. Just worth making. Okay, so with this, having said this, we now can do this for our theory of JT coupled to conformal matter. Anything else to say? Okay, yeah. So maybe one thing I'll say is that we should include the possibility of having several saddle points here. So we're going to be looking for all the possible solutions with a given boundary condition that satisfy this equation of motion sourced by the quantum stress tensor. Okay, so for JT, we want to be solving now this dilaton equation. This is the only equation that gets modified by including this this matter source. So first of all, we want to work out what this matter can look like. Write down an ansatz and then solve for that ansatz. It's going to be, of course, you have to sort of solve this equation coupled with the metric, and in particular, we have to solve it coupled with this Schwarzian mode, because that's going to determine how energy gets exchanged between our reservoir and our black hole. So the dilaton solution is going to affect the background on which the stress tensor propagates. It's the usual thing that we can't just solve them separately. We need to solve the coupled system together. And so we want to work out some ansatz for the stress tensor. So first of all, the trace, because it's a conformal theory for us, it's fixed by this Weil anomaly that we met last time. Just a minor technical point is that I'm going to actually set the trace of t to 0 by adding a counter term. So if you add a finite counter term to the action that's proportional to the volume of space-time, a cosmological constant term, then this gives a source that exactly cancels the trace of the stress tensor. This is just a convenience. It's basically the same as shifting, as redefining the dilaton with a constant shift, but so it's not not a major thing, but it's if you want to sort of follow along with the calculations at home, this is just a convenience. So now the more non-trivial pieces are these RR and VV components in this ingoing metric. So the important thing here is that we're going to assume the horizon is smooth. So if this is finite at the horizon at some time V0, then it's going to go like e to the minus V minus V0 times 2 kappa. So it's going to decay exponentially. This is the same thing we saw earlier, is that smoothness at some particular time means that it acts like these quasi-normal modes, if you like, and this stress energy dissipates. Essentially, it either falls into the black hole or it escapes out to infinity. So this very, very quickly gets washed away. And we don't, so for late times, we're going to be interested for times much bigger than this timescale 1 over kappa, on which the black hole settles down. What we're going to do is set this TRR equals 0. And this is going to be true for any state that's smooth at the horizon, or was smooth at the horizon for some length of time in the past. So the only non-trivial component we have to worry about is this TdV, but this is the ingoing energy. So this is going to be fixed by the incoming flux from infinity. And so this means, and in particular, it's some function of V, not a function of V and U. So this gives us a complete ansatz for our stress tensor. We have 0 outgoing stress tensor, and we only have to worry about this incoming piece. Fine. So with that, you can now go and actually solve this equation. So this is first of all the 2 of the components of this give us this very, very simple solution for the dilaton, where the dilaton is just given by the radial coordinate. I should say that this is not always true. If you had a non-zero value of TRR, this would be modified, but it's got this very simple. You have this very simple solution in the case where there's only incoming energy. And then the final component of this fixes the dynamics of the energy. So this is going to be recall the energy was, I think it was a half gamma times RH squared, where RH was this dynamical sort of horizon in the horizon radius in the ingoing metric. And it's telling us that the rate of change of the energy is given precisely by the expectation value of this stress tensor at the time t. Maybe I'll say it as a function of t. And now the expectation value of the stress tensor is something we can compute by using our Weil anomaly from earlier. So we're thinking about this circumstance where we have radiation in the far away in this reservoir system. So this is the incoming flux of radiation in this reservoir system. But then this other term comes from this Weil anomaly that we saw earlier. This combination of derivatives with omega. So you can go and compute this, and it turns out that it's just again given by this energy by sort of RH squared. This is telling us that the energy, first of all, it increases if you have stuff falling in from infinity, but then it also decreases, and this is the energy that's escaping as Hawking radiation. So this is very sensible, and this second term is telling us about the back reaction from the Hawking radiation. Okay, so there's a simple solution for the energy. It's just exponentially decaying with this constant. And we'll just say that this constant is, we're going to think of this constant as being very small. So gamma is, well, Yeah, okay. So this constant is much less than 1 over the time scales we're interested in. Well, yeah. Good. So yeah, the fact that this is small means the black hole is evaporating very slowly. So it's sort of an adiabatic process. Okay. And then the last thing we can do is actually try to solve this to the Schwarzian. So we had this formula last time for the energy. There was some constant. I can't remember what it was off the top of my head. But this was telling us that this is proportional to the function of the Schwarzian as a function of time. So this f is going to be an alternative way of expressing the solution. And we'll give a solution on the next slide. Okay, so where are we? We've got this, we've now constructed an evaporating black hole, or this particular subtle point to these quantum equations of motion. The metric is given by our ingoing coordinates, and now the horizon, this horizon radius is exponentially decaying as the black hole evaporates, and the dilaton has this simple relation with the radial coordinate. So this tells us about the gravitational fields. Now I need to tell you about the matter state. So one way of describing this is that if we took this flat metric with this capital U crystal outgoing coordinate and the small v ingoing coordinate, then it looks like the vacuum. So let's just explain why that is. So the fact that we're using this capital U crystal coordinate is saying that we have a smooth horizon. And it's also saying that that any excitations will decay like e to the minus 2 kappa t in the stress tensor. So this may not really be the vacuum at some early times. There's some star or something that's collapsing and forming a black hole. There is some outgoing stress energy, but you only have to wait a time, a few times 1 over kappa, and all that energy is dissipated, and the vacuum in any coordinate that's smooth at the horizon is going to be an excellent approximation at after a few times this time 1 over kappa. So this is a smooth horizon, and then in this v direction, this is telling us that we have an infalling vacuum. Okay, this pen's not working very well. Stay with the black. Okay, hopefully that's legible. So, so this is a description of our state that's at least going to be an exponentially good approximation after the initial formation of the black hole, whatever we use to prepare the state. So the important point here is that whatever happened when we formed the black hole we're going to forget about it very quickly, and it's not going to affect the dynamics very much. So we're going to be able to use this metric. So there are various things you could do. You could form a pure state black hole from collapse. You could start with some two-sided black hole and throw in some energy and let it escape. There's all sorts of things you could do, but it doesn't really matter what you've done at later times. Now, the other way of expressing is gravitational variables in terms of this Schwarzian, and this is useful for us because it's going to allow us to relate, in particular, this critical coordinate that's a coordinate that's smooth at the horizon to our outgoing coordinate that's calibrated with time at infinity, and the actual exact solution to this equation. So saying that the Schwarzian is this exponential decay, this equation has some slightly complicated solution in terms of Bessel functions, but it turns out that this solution is basically exactly right until extremely late times. So this actually solves a very slightly different equation that has some correction of order k squared, but this turns out to be an excellent solution, and you can go and again see the notes and check that so the Schwarzian of this is an exponential plus some tiny constant correction. And one thing to notice about this is we can expand this if t is some t0, which could be any size, plus a small correction delta t, which is short compared to the evaporation timescale. Then we expand this exponential, and the whole function. So this looks like an exponential of an exponential, but if we expand this, it becomes just an exponential. And this is, apart from this constant out the front, is exactly the same solution we had before for a static black hole. So in other words, it looks like a static black hole for any time period delta t much less than the evaporation timescale. So again, this is just saying the evaporation happens slowly. So for lots of things, this is a useful approximation. Okay, so this is a very explicit model of an evaporating black hole where we could really go and compute everything, and we're going to do that sort of towards the end of today. In particular, we're going to be computing entropies in this situation. Okay, now just one brief comment on various sorts of horizons that happen. So when we had our static black hole, this RH was telling us where the event horizon was, but that's actually no longer true in this dynamical case. Instead, RH is telling us the location of an apparent horizon, or another term for this is a marginally trapped surface. And the definition of this thing in the JT gravity context is that if you take the dilaton and shine a light ray outwards, then the dilaton is stationary. So we take d phi by dv at a fixed value of u. So this is saying, how does the dilaton change as I move outwards a little bit? And this vanishes. So the dilaton we should think of as, in a high dimensional situation, this would be the area of some transverse sphere. So if we're far from a black hole and we imagine some large sphere and we shine light outwards, then of course that sphere is going to get bigger. But if we're inside a black hole, we start with a sphere that's deep inside a black hole and we shine light outwards, then actually the sphere is going to get smaller in area because it's getting concentrated towards the singularity. And the place where those two things balance is the apparent horizon, or it's a marginally trapped surface. So just a recollection that this would be the area in higher dimensions. Fine. So instead, we have the event horizon, and in our sort of light cone coordinates, this corresponds to this outgoing time going to infinity. And again, you can sort of exercise is to go through the various equations we had last time and work out. So in particular, you can use this reparameterization and plug that into the solution for, we had a change of variables between this reparameterization and the coordinate r last time. Or you could just plug that in, it's straightforward exercise, and you find that the event horizon, that is to say the actual surface of last escape, lies slightly inside the apparent horizon. So usually in classical gravity, for most circumstances, then the event horizon, or all the way around, then this apparent horizon, or a marginally trapped surface, or a trapped surface, is going to be inside the event horizon. And this is sort of one version of the Hawking-Penrose singularity theorems is saying something like this. And but this needs energy conditions. So in particular, the null energy condition, which we'll mention in a second. Okay, so there's an exercise in the notes, which is actually just to check that this is true in JT gravity, and that's to take some null vector with some parameterized by some affine parameter, and to find the divergence of a null congruence in terms of the derivative of the dilaton along this outgoing null vector, And there's an analog of Ray-Choudhury's equation, which tells you about how areas focus in JT gravity. So there will be another term here in higher dimensions, but it's kind of simple. In particular, you've got this null energy condition that tells us that the energy density measured on a null ray has to be positive. And you can use this to show that apparent horizons always lie in event horizons. But here, of course, this is violated. Our apparent horizon is outside the event horizon. And in fact, this for us is going to go something like a TVV, or rather an expectation value of TVV. And this is going to be negative at the horizon. This is what we saw earlier, is this, you get this negative piece from that's the counterpart to Hawking radiation, if you like. So we violate the null energy condition. Now, this is extremely important to allow the black hole to evaporate. And this also, for example, is necessary so we can violate Hawking's area theorem, is the fact that we're violating energy conditions by quantum matter. Okay. So last few comments about black holes before we about this black hole before we move on. So far, we've really just been computing the dynamics of stress energy in this black hole. And for example, we can take this saddle point now and just measure the 1-point function of the stress tensor at infinity, and it tells us that now the temperature of Hawking radiation will change over time and so forth. But we can really compute lots of things. So this saddle point that I've given you just now is a starting point for perturbative calculations of all sorts of, say, expectation values in the radiation. But the basic conclusion, I won't sort of belabor the details. The basic conclusion now is that we don't just determine the stress energy to look like thermal radiation, but really the state itself will look thermal. So in particular, it's going to be a mixed state, and we'll quantify this a little bit more. So the entropy. So I'm talking here about the von Neumann entropy, which we're going to introduce in a moment. And in higher dimensions, if you let your black hole evaporate entirely, this doesn't really happen in the JT context, because you just have this exponential decay of the black hole. And at some point, when the black hole gets small enough, the Schwarzian mode becomes strongly coupled, and then you sort of lose control of what's going on. But in higher dimensions, it's reasonable to let the black hole evaporate entirely. Then you have this pure initial state, perhaps, that formed the black hole, and it ends up with this mixed state of Hawking radiation. And this is, if you think about this, for example, in terms of an S matrix, you have some ingoing matter that's pure from scry minus that forms a black hole. Then the outgoing matter, this calculation tells us, at scry plus is mixed. So there's not really a conventional S matrix to describe this. It describes the evolution of a pure state on scry minus to a mixed state on scry plus. And the underlying reason for that is sort of clear in this calculation, is that our Penrose diagram of our black hole looks something like this. So we have our initial pure state, psi in on past null infinity, and then we have on scry plus we have some mixed state Ray Hawking, and the reason it's mixed is because we have this because scry plus doesn't form a complete Cauchy surface for the space-time, and we also have some mixed density matrix for the interior. And Hawking radiation is creating some large amount of entanglement between interior modes, between the interior of the black hole and the Hawking radiation. So this goes to a pure state on H scry plus, tensor H say interior. And the state just on Scri plus is going to be mixed. So this is strange, certainly, but by itself is not immediately a problem. But we're going to sort of dig into this a little bit by making this more quantitative. So we're going to talk about quantifying how mixed the state is, the state of radiation, and we're going to try to sort of sharpen the problem here. And this is the origin of the information problem. Okay, so the next step is going to be talking about entropy, and we'll make, once we've just sort of discussed entropy and quantum systems in general, we'll come back to our evaporating black hole and make use of some of these things. Okay, so any questions before we move on? Sorry, it's sort of going through that construction is sort of preliminaries to that we'll make use of later. But.
Sorry, I have a silly question. Yeah. Okay, I'll go ahead. It's just a silly question about the splitting of the Hilbert space. If you let the black hole evaporate completely, why is there an interior Hilbert space still?
Yeah, well, this is just so our the level of the approximation we're making. Or I should know. We're essentially treating the metric as being something classical, and we're allowing it to be sourced by this expectation value of a stress tensor. So at least at the subtle point, we have this notion of a space-time, and we can think of the state as being quantum fields propagating on that fixed space-time. It's going to be, there'll be some sort of fuzzing out by the fact that the space-time itself isn't quite fixed. We're not going to go into, but it's just doing it at the level of quantum fields on a fixed background. And the fact that a background is dynamical will change the quantitative details of very fine, careful measurements, but the qualitative picture is the same. And if you, so this Cauchy surface, the union of the red guy and Scri plus, is sort of disconnected. So there's this spatial null infinity up here. Is actually, if it's going to evaporate entirely, I should probably draw something different. There'll be a new origin up here. Yeah, so and there's something singular going on here that we don't know about, where quantum gravity effects become important. This is one reason why this formulation, just pure states evolved to mixed states, is not a terribly sort of sharp and worrying version, because we don't know what happens at the end point. So maybe something there evolves, sort of resolves things, and but the version that we're going to talk about later is going to be resolve that.
Just to understand well, I mean, at this point, exactly, once you draw that Penrose diagram, I would naively think I can draw a Cauchy surface that goes all the way to late time. It doesn't meet anymore the red thing, and so I should get a Hilbert space there.
Yeah, you can draw a Cauchy surface at some earlier time. Yeah. The only point I'm making is that Scri plus, the stuff you catch at infinity, and maybe Scri plus with the union of time-like infinity, is not a complete Cauchy surface. That's the only.
I get still this disconnected piece. Okay, thanks.
Hi, Henry. I had a question. I think you already commented. So when the black hole evaporates entirely, then if you think in terms of this half line coupled to a quantum dot, like you were explaining yesterday. So what is the vacuum, the description of the vacuum of this quantum dot is something that you can describe in JT gravity or not?
Yeah, so in JT gravity, you don't really have this complete evaporation. So, actually I've scrubbed it out from last time, I'll just say it. So we have this parameter gamma, which is dimensionful. It's got dimensions of inverse time or dimensions of energy. And roughly it tells you, it's like a QCD scale. It tells you the energy below which coupling gets strong. So really, in terms of the semi-classical thing that I've presented, the energy is going to exponentially decay away until it becomes parametrically small. then the Schwarzian mode becomes strongly coupled, and the semi-classical approximation I talked about isn't valid anymore. And yeah, then it would just sort of evaporate exponentially away forever. So it's if you extrapolate it, so it doesn't really evaporate in this context, but you'd expect some other physics to take over, and in fact, things like topology change become important at very low temperatures as well.
But can I just compare, say, with higher dimensional? I mean, in ADS CFT, if I take ADS 5, I can put a black hole, and if I let it evaporate by coupling it, I will still go through like Planck scale black hole, which I don't know how to describe, but I can describe the vacuum by itself, just vacuum without. So here it seems to be harder than that. If I understand correctly.
Yeah, so I mean, in JT, you could sort of formally describe the vacuum as like a Poincare ADS, but it's not really, yeah, what's a good way of, yeah, if we're thinking about this as an approximation to what's going on in the near horizon of near extremal black holes, for example, then the approximation is breaking down and things, and there'll be some new effects that are important. For example, we can't really distinguish between whether there's an exact ground state degeneracy or whether there's just a sort of smooth drop off of the density of states. But yeah, okay, these are details that depend on precisely what you want to study at the endpoint of evaporation. And in the end, we're going to avoid talking about the endpoint. So,
okay, thanks, Aaron.
Yeah, I'm not really sure I answered the question, but I'm going to evade it anyway. Yeah, maybe one more way of saying it is that once we go to the once we let the black hole go to very, very small energy, then the value of the dilaton at the horizon becomes sort of very, well, okay, maybe I won't commit to any live. So we're going to just very quickly now talk about entropy in quantum systems in general. So I want to have in mind now, so of course we're going to eventually apply this to our black holes and sharpen this sort of tension that we briefly mentioned at the end there. So I want to imagine here some ordinary quantum system. So maybe we have some box that contains a load of photons, and there's a little hole in our box. Conveniently, my drawing is bad enough that there's already a little hole and some radiation escapes. So I'm going to call the box is going to be some system A, and the rest of the world is some system B. And we're going to be thinking about what happens for an ordinary quantum system like this. And we want to talk about the entropy to sort of quantify how mixed the state is to make this statement about the entropy of Hawking radiation more quantitative. So there's the main sort of entropy we'll be talking about is sort of fine-grained entropy. So for any density matrix, we can define the fine-grained entropy, the von Neumann entropy, as this minus trace of rho log rho. One example of this is if in a situation like this, perhaps if our system is bipartite and we have a pure state on the whole system, then if we throw away the degrees of freedom in B, for example, we're just left with the degrees of freedom in A, then this von Neumann entropy of rho A, which is equal to the von Neumann entropy of rho B, is telling us about it's quantifying the quantum entanglement between A and B. So this is the familiar entanglement entropy. But this is fine-grained because it depends on very detailed information about sort of long-range correlations, and it really cares about the detailed correlations in the state. But this is not the sort of entropy that we encounter, for example, in the second law of thermodynamics. So if, for example, we do time evolution, which means we conjugate the density matrix by some unitary. So maybe for an isolated system, we do time evolution, then this von Neumann entropy doesn't change. So it doesn't obey a second law. So it's not the usual sort of entropy that we encounter when we first learn thermodynamics. Instead, we need some notion of coarse-grained entropy, sort of a notion of thermal entropy. And one precise way to define this is you take some set of subset math BDO of macroscopic observables. So these are this is a choice. There's many possible different choices I can make. I'll talk about what a good choice is in a moment. And you could define this coarse-grained entropy. So O is a coarse graining. Is a set of observables I have access to that's not all observables, as only some subset. And you take all possible density matrices, row twiddle, that have the correct expectation values for these coarse-grained operators. And then out of all these possible density matrices, which they can differ from your original density matrix in details, but they have to be the same for these macroscopic observables, is you maximize the von Neumann entropy. And in particular, this means that I can uniquely, is an exercise to check that you can't have two different maximizers. This is unique. This is to do with convexity of entropy, but you can have a coarse-grained density matrix here, which is the density matrix of maximal von Neumann entropy that agrees with my macroscopic observables. So just a couple of examples here. One is that you just take your set of macroscopic observables to just be the Hamiltonian. So this is good in if we're in equilibrium. This is a useful notion of entropy. And of course, we end up with a density matrix that's just the usual Boltzmann distribution. And this is because of our sort of no-hair theorem and the fact that our black holes are, you have this sort of quasi-normal mode decay, that it sheds all the details about what formed the black hole apart from conserved quantities. So for us, it's just the energy. It might include charges, angular momentum. So this is maybe a good, a useful notion for a black hole. So for example, we briefly mentioned the Bekersine-Hawking entropy that we defined from the first law last time. So we might hope that we can interpret the Bekersine-Hawking entropy as this sort of a coarse-grained entropy, and we'll give some other reason why you might expect that later. A maybe slightly more fine-grained version is you take your set of operators not just to be the total energy, but local energy densities, and so this is maybe it'll be something like you get in hydrodynamics. So this might be useful for radiation, because the radiation doesn't equilibrate globally. It's sort of freely propagating, but it sort of locally looks like an equilibrium state over short periods of time. So it's useful to use this sort of notion where you let the energy change with time. Well, okay, I'll define what I mean by useful first. So what's the point of introducing these coarse-grained entropies? In the end, we're mostly interested in these fine-grained entropies to quantify this information problem. But the important thing is that if I do a coarse graining, so here O is coarser than O primed because it contains fewer operators. So if I throw away more information, then entropy increases. This is sort of completely manifest from the definition. I'm just, if O is smaller than O primed, then I'm maximizing over fewer constraints. So I, of course, get a bigger maximum. So we can always do this. And an extreme example is when O primed is the set of all observables. If O primed is the set of all operators, then this just reduces to the von Neumann entropy, and we have this bound. So in this entanglement example earlier, in particular, this is going to be very useful, is that the entropy of rho A, which is the entropy of rho B, this entanglement entropy, has to be bounded by, in fact, the minimum of some coarse-grained entropy of rho A and some perhaps different coarse-grained entropy of rho B. So we actually get, in this context of entanglement entropy, we get two bounds. And now I can tell you what I mean by a good coarse graining. A good coarse graining, well, I'll just say it in words. A good coarse graining is one that makes these bounds as tight as possible without including extremely complicated details. So you might think of a good coarse, of our coarse graining O is as giving the set of observables that in whatever situation that we're in, the set of observables that don't equilibrate. So in our black hole, it completely settled down apart from the conserved quantities, so we can just keep the conserved quantities. In our radiation, the energy density that's emitted early is going to be a different temperature from the energy density that's emitted later, so they're locally in equilibrium, but not in equilibrium together. So something like this, the local stress energy is giving you the set of observables that don't equilibrate. And this will give you the sort of sharpest possible bounds without having to dig into the fine-grained details of the state.
So there is a question in the chat. Is it possible to throw away too many operators while coarse graining? So that's
yeah, absolutely. So this is the point I made here, is if you do something that's too coarse, then it's just going to be less useful for this bound. So for us, there are lots of reasons you could be interested in this. You might be interested in trying to come up with a macroscopic derivation of a second law or something. So there's all sorts of things you could be interested in here. For us, we're interested in getting a really good bound. And if you coarse grain too much, then the entropy increases too much and this bound becomes not so useful. So that's the only reason we're going to use it. Fine. Yeah, so for example, if I just took the radiation and used its total energy, this would give me a less good bound on the entropy because I could get a higher entropy by spreading the energy out evenly rather than having this spatial dependence. Okay, so now we can use this to introduce this page graph. So we have this system which is bipartite. It's got two pieces, A and B. A is going to be our black hole and B is going to be our reservoir later. And we started off in some excited state. So there's some energy that's sitting around in here in some pure state, and there's no energy in the reservoir. And then we're going to let time evolve, and energy is going to pass from A into B. So some of these excitations that were over here, we're going to start moving into the reservoir. And there's going to be some mixed state, and we're going to have we'll have some mixed density matrix, and these things are both going to be mixed. And then eventually, we're going to imagine that this reservoir is very, very large, so that all of the energy that's initially in A is going to escape into B. And we just have all the energy in here. A is cooled down to its ground state, perhaps, and we've got some final state in B. So this means that S at time 0 is going to be 0 because there's no energy over here, and S at T final is going to be 0 because A is now in a pure state. We started with B in the vacuum and we end up with A in the vacuum. So this is an example of saying that in quantum mechanics, the pure states, initial pure state of the black hole should evolve into a final pure state in the radiation. Okay, but we can be more quantitative. So in particular, we can use this. We can use these bounds we had earlier. So first of all, yes. So I was being sort of semi-explicit about what these coarse grainings were last time. I'm going to just sort of assume we've fixed that, and I'm going to call this coarse grained entropy a thermal entropy. It doesn't necessarily mean like an equilibrium thermodynamic canonical entropy. It just is a generic term to mean there's some coarse grained entropy. So we have this so this first curve here is going to be the entropy, this thermal entropy of the B system. So this is in the context of our radiation, it looks roughly thermal. So in the Hawking radiation, we can add up all the local entropy density, and we get some curve like this. And this similarly is the thermal entropy of rho A. And now the actual von Neumann entropy, S of T, which is the entanglement entropy between the two, is bounded by the smaller of these. And in fact, if our coarse-grained entropy is a good measure and everything else is equilibrated, then we expect the actual answer to very, very closely follow this, the sharper bound. So this black curve is what we expect for the von Neumann entropy. I won't go through the detailed arguments for why we expect that to be true, but roughly speaking, we expect the whole state to be generic under the constraints by the thermal entropy. And there's a little bit more in the notes that somewhat justifies this, but in some sort of chaotic quantum system, we expect that we essentially saturate one of these bounds. Okay, so that's what we expect of an ordinary quantum system, and this was introduced in the context of black holes by Don Page. So this black curve of up and then down is called the Page curve. It's got this fairly sharp transition here, and this transition happens at the so-called Page time. Okay. Oh, there was one feature that I should have made that I didn't do very well here. I might just briefly point out, which is that the final thermal entropy is going to be larger than the initial thermal entropy. So that's the second law of thermodynamics, essentially. And again, we'll see this in our example. And this does place an important constraint on the black hole physics as well. Okay, so now we're just going to briefly talk about entropy in quantum field theory. I've gone on ahead. When did I start? I just want to.
I guess you have like 7 to 8 minutes.
7 to 8 minutes. Okay, so let's very quickly talk about entropy in quantum field theory, and I think we'll set up our sharp paradox by the end of today. Okay, so we'd like to be able to compute some of these von Neumann entropies in quantum field theory. For example, with the radiation. This is kind of hard to do directly, but the trick here is to compute, instead of this, because this log is difficult, to compute integer powers of the trace of the integer powers of the density matrix. Hopefully this is going to be familiar to many of you. This is the so-called replica trick. So one way of doing this, which people have been doing in context for a long time, is to talk about these Renyi entropies, particular function of these. And once you've computed this for all integer n, you can hope that there's some sensible analytic continuation to real n. So there's a step here, continue to real n bigger than 1, and then take the limit. And okay, there's various things you can say about constraining what this continuation should look like, but let's not go into the weeds on that. There is another method that I won't describe in any detail, but just briefly mention, which has been recently used to good effect, and in some ways is more principled, which is to consider instead this this quantity called the resolvent, and you can expand this as a sort of geometric series to write it in terms of integer powers of rho. And if rho is a density matrix, this is guaranteed to converge, and then we'll have a unique analytic continuation, and you can use this to extract, in fact, more details than this. You can really extract the spectrum of rho, essentially the discontinuity as across the of when lambda is positive and imaginary and negative and imaginary. There's some discontinuity that tells you about the density of eigenvalues of rho. Just thought I'd briefly mention this as something nice, and this is the so-called West Coast paper, for example, uses this in the context of a model of evaporating black holes. It's not exactly what I talked about today. So this is by Pennington, Schenker, Stanford, and Yang. And you can, once my notes are up, you can find references there. So this is just something to point out as an alternative. Fine. So I just want to say one more word about this sort of replica trick. Is this has an interpretation which is operational in terms of experiments. So if you just do an experiment on a single copy of a state, you can never actually tell whether it's, say, a mixed state or some unknown pure state. This is, of course, exactly the same thing. So you can never tell with one experiment. If someone just hands you a state and says, can you tell me whether this is pure or mixed without giving you any other information, then you can't tell with, you can't say anything at all about that question. But if someone gives you two copies and says, I give you two copies of a state which are identical, can you tell me whether it's pure or mixed? Then you can give them some information. So one way of thinking about this replica trick is you take n copies of your state rho. So you form this n copy state, or n replica state, if you like, and you compute the expectation value of this permutation operator. So this is pi, so let's say pi 2. This is often called the swap operator of some state psi 1 tensor psi 2. It's defined as psi 2 tensor psi 1. And more generally, these would be defined by some cyclic permutation. So this is, so one way of thinking about the replica trick is that, which will be useful for us later, is that it's telling you about the expectation value of a particular operator that you can measure. And in fact, this tells us something about how we often compute these things in practice in quantum field theory, which is, you can think about this in path integral language, is that we take two copies of our state. So maybe we've defined some state in the past. So this is some psi initial on the whole system. This is system B and this is system A maybe. And this top piece of the path integral defines the sort of bra piece. And then we trace out B. So you can think of this little cut here. If you inserted some boundary conditions for fields, this is computing the matrix elements of this density matrix rho A. And we do that twice, and then we join them together in this way. And this is just contracting indices to compute the product of matrix elements and the trace. Good. And you can really think about this in terms of an expectation value of an operator. Again, very physically, we're defining our state, and then this swap operator is just a thing that that defines this sort of non-trivial way of gluing things together. Okay. This is, we'll just need this at the sort of level of pictures, but okay. So that is everything I was going to say about entropy in general. And in the last couple of minutes, we'll just mention how we'll do our first calculation in the black hole. Okay, so I guess we'll crack on with it. So the only thing we're going to need to know about conformal field theory, entropy in conformal field theory, is how it behaves under these Weyl transformations. So yeah, I guess yeah. So the important thing only is this sort of Weyl anomaly piece. Oh, I guess this is. I guess I said this already. Is that if you were to compute the entropy of some state in a Weyl transformed metric, then you get the same result as if you computed the entropy before the Weyl transformation up to this this piece here. And you could think of this as, if you like, as being related to changing the scale of the cutoff of the theory. If you're, we'll talk a little bit about the UV divergences, and the way you cut those off will change if you do a Weyl rescaling. I'm wondering if yeah, I've got two or 3 minutes, or should I can either wrap up here or take 2 or 3 minutes.
You can take 2 or 3 minutes, but
thanks.
But okay. How long do you really need?
No, okay, I'll wrap up here. Yeah, let's
yeah,
okay.
Maybe it's
we set ourselves up for entropy, and yeah, okay. We've said everything we need to know about entropy and quantum field theory, so we'll start computing entropies at the beginning of tomorrow in our gravitational theory. Okay.
Okay, thanks, Henry, for a nice lecture. Yeah, let's thank first. Yeah, any questions?
Yeah, maybe I'll ask one. So there is a bound on entropy you can find easily by using that the relative entropy is positive, right? This gives you a bound in terms of the expectation value of the modular Hamiltonian. Do you know how that compares to the bound you're drawing there?
Let's see. I guess that, so this is something like, so you want to, yeah, this may be related to, well, okay, that requires 2 states. You want to know about the relative entropy between the, between the actual state and some, maybe the thermal state, for example, and some coarse grained state.
Right. For instance, I'm thinking about the vacuum. I mean, one state I take to be the vacuum, and the other is like the excess entropy due to the radiation, right? Let's say I'm in the reservoir and I want to measure the entropy of the radiation. I want to subtract the one of the vacuum, and so that's bounded by the expectation value of the modular Hamiltonian in the vacuum. Sorry, in the state, but the modular Hamiltonian of the vacuum. Yeah.
Yeah, I'm not sure I can mention any details in real time. That's probably, yeah. So the way I'm talking about it, there's some slight subtlety as to precisely what you do with subtracting the vacuum and so forth that I'm going to sort of brush over. But using relative entropies is makes that more precise, and you end up with finite things. So yeah, I don't have anything terribly concrete to say, but
okay. So you don't know if it's expected to be close to the optimal bound, or if it's expected to be way up. That's fine. It's just curious. Thanks.
Yeah, I have to. Yeah, I don't have anything that I want to commit to immediately. I'll think about it. I'll let you know.
Any other questions? Can I ask one question about the swap operator? So for the computation of the Renyi entropy, you just need the cyclic permutation, right? And is there any like a use of other swap operators?
Yeah, so a general permutation here, it doesn't actually give you anything new, because you can always at least in this context, because you can always, you decompose a general permutation into a product of cycles, and each cycle then falls into its own piece. So you just end up with a product of cyclic guys. Yeah, if your sort of n state was not just an n-fold tensor product, then you might get something that's slightly different. But at least in this context, it doesn't gain you anything new.
Any other questions? Okay, I guess people can also ask questions in the Slack. So for now, let's thank Henry again.